So, here from today's lecture onwards in the third week, we are making a slight change in the main ideas that we have been discussing till now. Our main idea that we have discussed in the last week was portfolio optimization, which says how should we make our investments, what investment would give me the maximum return with the minimum risk. That was the clean idea. But here we will be talking about pricing. So, how do you price an asset? How do you know what should be the relation between the return on the asset and its associated risk? What are the relationships? So, these concepts come under something called capital asset pricing model. Then we are talking about the capital asset pricing model that we are going to talk about now, essentially relates the risk associated with a single asset with its return. Because here we had been lastly we were just looking at not the relationship between the risk and the return, largely we were looking at minimize the risk and get some return. To do this, we have to introduce something called one fund reserve, one fund theorem. So, what is this one fund theorem all about? See, when investors invest, they do not invest all in risky assets. It is not a good idea to invest everything in risky assets. You have to have some risk free assets like a bond or a fixed deposit, something like that, so that some part of your investment has a sure return, right. So, what would happen if I add an risk free asset? So, added with your portfolio, I will have one more asset, the risk free asset. So, now your portfolio, new portfolio will have a risk free asset, say asset number 0, and then you will have the risky assets. So, now you will have n plus 1 assets, right. So, risk free asset has a rate of return RF. See, it is something like interest rate, risk free asset, risk free. So, rate of return of the risk free asset. So, with this asset is risk free. So, if we invest 1 rupee in this asset, then the next in the next trading period you will get 1 plus RF. Now, we want to say that of our money, an R bar is the expected rate of return. This is a fixed thing. So, this is the expected rate of return of the portfolio of risky assets. So, what is the covariance between this risky asset, risk free asset and this part? This covariance is actually 0, because if you observe it very correctly, then this is nothing but rate of return of the portfolio minus its expected return into rate of return minus expected return. This is constant here. So, this is 0. So, covariance between the 0 asset and the remaining portfolio, which I write P for example, is actually 0. Now, if you look at that, what is the mean? So, what is this RF? Here sigma of F, there is no risk, it is a 0 risk portfolio, a 0 risk asset, sigma of F is 0. So, now if I have a optimal portfolio, right, if I have a portfolio in which I have made an optimal investment, then if I add a risk free asset and I change my weights a little bit, can that investment remain optimal? That is the question. So, if I now look at the mean of this portfolio, say portfolio P tilde. So, if I look at the mean of P tilde, what would happen? Suppose of the total money I give alpha I have invested in the risk free portfolio and 1 minus alpha I am invested in the risky portfolio. Alpha in the riskless asset and this is in the risky portfolio. So, my mean is and what would be my standard deviation? Standard deviation P tilde is alpha, of course, it will be the same sigma f. Sigma f is 0 actually. So, if you just look at that, so sorry there was a mistake here, it would be sigma r bar, that we have done earlier also, sigma r bar diagram. So, here sigma is 0. So, he is RF is some riskless portfolio and P is the risky portfolio. So, basically now as alpha varies you trace a straight line between P and R. This is nothing but the convex combination, those who have some idea about it. You need not get so worried about it, but it traces a straight line. So, this becomes now the efficient frontier. So, if P is an optimal allocation on the portfolio, then I can change the weights a bit, right, and I can put some money in the risky asset and then I can put the remaining money in a risk free asset and still get an optimal portfolio, which you can prove by yourself, which I am not getting into. So, you can always construct a efficient portfolio by combining a portfolio of risky assets with risk free assets. So, this is called the one fund theorem, which says there exists a portfolio which is also called a fund. So, this is called the one fund theorem. So, there exists a portfolio of risky assets with whom you can have the combine a risk free asset in order to generate a efficient portfolio, right. Which, so this if you look at it, it simplifies the efficient frontier very much, it makes it a straight line, right. Now, the question is what should be this P? This question is answered by the capital asset pricing model. They say that this P, this set of risky assets must be the market portfolio. It must be the market portfolio means you have to invest in all the market, all the available instruments, all the available risky assets in the market. So, if you cannot say that I will invest in only couple of them and do not invest in others. So, if you take the market portfolio, that is what the capital asset pricing model says, that if you take the market portfolio and if you take a risk free asset, you can still generate an efficient portfolio, rather optimal portfolio, right, which will give you the minimum return and the risk. Of course, the mathematics can be done in a more detailed way using optimization like we had done earlier, but we are not going to get into the details. So, P is equal to the market portfolio, which we write as M. Our job would be now to show that given my market portfolio, what is the expected return? Now, I have a risk free asset also. So, risk free asset I do not need to bother about expected return, I will know what is my expected return, it is fixed. And I know that sigma f is 0. But with the remaining part of the portfolio, which is the market portfolio now, there is a question of expected return, there is a question of risk. How is that expected return and risk varies, that can be beautifully described once you put in a risk free asset in your combination. So, now that is the starting of the capital asset pricing theory, and that is what we are now going to describe. So, now we are going to again look at the R bar sigma bar model. R bar sigma model. When sigma is 0, let RF be the rate of return in the risk free asset. See, the rate of return of a risk free asset is always lower than the rate of return in a risky asset. That is why people put money in risky assets. If the return was same, then I need not put money in risky asset, I can put in risk free asset. So, the market portfolio is a portfolio whose expected return of rate is something like here, and it has some standard deviation. Now, join these by a straight line segment. In fact, like this, you can think the line. So, this is my sigma m risk associated with the market portfolio, and this is my R bar m, the expected return of the market portfolio. This line is called the capital market line. This line joining R bar and m, this line is often referred to as the capital market line. So, let me try to find the slope of this line. So, the coordinate here, this coordinate here is 0 RF, this coordinate actually, and this coordinate here is sigma m Rm. So, what is the slope of this line? So, if I take any point here, any point say here or any point on the line, does not matter, I am just taking here. So, I am taking an arbitrary point here whose expected return is some R bar, sorry, whose exposure to risk is given by sigma, and R bar is the expected return. Now, how do I relate this? So, I take any portfolio, we are risky portfolio, and I am relating the things. So, if you write down the slope, so slope of this line can be either calculated through these two and also through these two. So, if you do that, then simply that calculation will show you that R bar is equal to RF plus, so R bar minus RF divided by sigma minus sigma f, y axis y coordinates difference by x coordinates difference ratio, that is slope, but here sigma f is always 0, sigma f is 0. So, then that will give me, again you take this one, so I should write it in this way, R bar m minus RF by sigma m, this whole thing into sigma. So, here given any portfolio which is on the market line, of course sigma and R bar, these are all non-negative numbers, right, I mean, you cannot have sigma negative, so they are all here, right. So, anything that you choose here, any other portfolio that you choose on this line, on the ray basically emanating from R bar, will satisfy this equation. So, this equation shows how given a portfolio, and if you choose a risk free asset, how for any portfolio the expected return is associated with this risk. The portfolio optimization that we had studied does not say the relation between R bar and sigma. So, once you induce, once you induct a risk free asset, it becomes a very simple equation. We are now going to look at what is called the pricing model, right. We are now going to talk about something which all investors talk about, the beta of stocks. We are going to introduce this, and that will be the thing that we are going to talk about in this discussion. Okay. So, in the pricing model, it is called the CAP or the CAPM model. Our job is to relate the return of a given stock, given asset, say ith asset, to its actual risk. So, how is the return of the asset I is related to its risk, that is sigma I, right. So, that we are going to do. So, in this case we assume that the market portfolio M is an efficient portfolio, and if you take the whole market portfolio, you can always make, you will always get a solution to that. Of course, technically if you look at, remember last discussions where we have taken the variance covariance matrix to be, for obviously proper reasons, to be strictly positive, positive definite, then you are getting one efficient solution. So, you can always make the market portfolio efficient. So, now let us write down the theorem which we are writing down from Leuenberger's book, Investment Science. So, we take an asset I, again I will tell you, and I am relating it with the asset's expected return with its risk exposure, that is sigma I. Let M be the market portfolio which is efficient. And Ri bar is the expected return of the ith asset. Then this is true for any I. Then Ri bar minus Rf, this is equal to beta I into R bar Rm bar minus Rf. And what is this beta I? This beta I is called the beta of the stock, which is a very important indicator for practitioners. Is the covariance of Im, that is sigma Im, covariance between the single asset and the market portfolio itself, sigma Im divided by sigma square M, the variance of the market portfolio, which I can also write as covariance Im divided by sigma square M. So, here see, in this situation we are assuming that everybody is a mean variance optimizer. When somebody calculates betas, usually in the market, everybody assumes that everybody has is a mean variance optimizer, and everybody knows that all the stocks, the rate of return is same, and everything is assumed to be same. So, for everybody, every parameter is assumed to be same. Only under these ideal conditions you are getting this. So, we are going to try to give you a proof of why this is so. How do we get this formula? And the beta I is a very important indicator. It tells you, it relates the asset here and the risk of the asset I with, right, it relates the risk of the associated with the asset I with the risk associated with its own relationship with the market portfolio in relative to the market portfolio. For example, if you look at this one, this term R bar M Rf by sigma M, this is often called the price of risk. Because it tells you how much, what is the change in your expected return if you increase your risk by one quantity. So, here suppose I have R bar is Rf plus this price of return, this R bar M minus Rf by sigma M into sigma. Now, I have R bar dash, which is Rf plus R bar M minus Rf sigma m into sigma dash, where sigma dash is say sigma plus 1. Then r bar minus r bar dash minus r bar is nothing but r bar m minus rf by sigma m. So, it shows that this actually tells you how much change you are expecting in the expected return, right. So, if you increase your risk, because this is positive, Rm bar is always bigger than Rf. So, if you increase your risk, right, your expected return increases. If you decrease your risk, your expected return decreases. So, this simple line, straight line actually explains a lot of things about the market, and that is the beauty of this this whole analysis. Now, how do you come to this conclusion? And that is exactly what we are going to prove now. And with that, we will finish this very basic study of capital asset pricing model. After which, we will start our study of option pricing. So, we know that the market, assume that the market portfolio is efficient. So, which is associated with addition of the risk free rate of return, which is RF, and if this is the market portfolio, then this is the capital market line. Now, I take any asset I. Now, let me forget about RF for some free risk free asset. Take an asset I, put in alpha amount of your money here, and in the market portfolio put in 1 minus alpha. So, in this new system, you have taken some asset I, and the remaining market portfolio. See, this is a very strange system. You might say, okay, why are you doing this? Because your asset I must be within the market portfolio. No, basically then I am additionally putting an alpha on the asset I. am keeping it separate and looking at the market portfolio as a separate. I am basically looking at market portfolio as if it is a single asset. Then if I do that, so you could change the alpha 1 minus alpha, that is up to you. So, r bar alpha now with this I and m would be alpha time r bar I plus 1 minus alpha time r bar m, and sigma alpha, just I am writing the standard deviation, would be alpha bar square, alpha square sigma I square plus 2 alpha 1 minus alpha sigma I m, the covariance between I and m, plus 1 minus alpha square r bar, or sigma m square. So, I am just writing in the next line so that it makes it more clear. 1 minus alpha square sigma square m. So, this whole thing to the power half, we have taken a square root. So, that is what you have. So, now as alpha varies, you can vary the alpha. So, you can have the portfolio I must be having originally this Ri and sigma I, right. And as you vary the alpha, this has to, so this is the capital market line, this M. So, this r bar alpha sigma alpha would actually trace out a curve. When alpha is 0, this is nothing but the market portfolio. So, at alpha equal to 0, the curve should touch the market portfolio, and then this is the asset I. So, alpha equal to 1, it is the asset I, right. So, you can vary alpha accordingly, it could be negative also, short for short selling. Now, you see this curve cannot go over this capital market line. If it goes over this capital market line, then there is a big problem. The problem is the following. The problem is that then basically you are there could be inefficient portfolios which crosses the efficient portfolio, because none of the inefficient portfolio paths can cross the efficient portfolio, efficient frontier, because this is the efficient frontier. Then it violates the fact that M and RF both are on the efficient frontier, it violates the fact. So, what happens is that at M this curve is tangent to the capital market line, that is what should happen. So, once that happens we can start thinking about that. Now, we can do the derivatives, and so which means the slope of this curve, slope of the tangent, slope of the capital market line and the slope of the tangent rather and slope of the tangent to this particular curve given by this parametric equation must be the same. So, once you can do that you will get the answer. So, let us just do it. Just rub this part for a while, I am sure you have copied it down. So, let us go and do the step by step proof. So, d r bar alpha d alpha. So, that will give you r I bar minus r m bar, this is what you will get. Now, d of sigma alpha by d alpha is, I will just write down the expression because this expression I do not want to keep on computing the expression. So, but we are essentially looking at the slopes at M. So, everything has to be calculated at alpha equal to 0. So, at alpha equal to 0 these remains same, does not matter. So, d r bar alpha at alpha equal to 0 is r I bar minus r m bar, but d sigma alpha by d alpha is equal to, put alpha equal to 0, right. Once you put alpha equal to 0, it will give me sigma Im, it will give me sigma Im minus sigma square, sigma m square divided by, because if you put alpha equal to 0, it will be 1 into sigma Im, alpha equal to 0 will be minus, here it will be equal to 0 divided by sigma alpha. So, now this is the formula when you put d alpha, alpha equal to 0, because sigma alpha when you put alpha equal to 0 it just give sigma m, because this is a calculation of the square root, right. This is sigma alpha, okay, I am writing it in a much more. So, this is because 1 by 2 root alpha into the chain rule basically. Now, once you have this, you want to compute, but you want to compute, know the relation between r alpha and d alpha. Basically, you want to compute d r bar by d sigma alpha, that has to be computed at alpha equal to 0, which now is the ratio of this by this, and if you take the ratio of this by this, it will, so that is exactly the slope of the tangent to the curve defined by r alpha, the r alpha bar and sigma alpha. And once you do that, what you get is sigma m into r I bar minus r m divided by sigma I m minus sigma m square, this is the comma I m. So, this is what is happening, this is, but this must be same as the slope of the capital market line, the tangent line, and you know what is the slope of the capital market line, the slope of the capital market line. So, then this must be equal to r bar m minus r bar f, r f by sigma m. So, these two quantities are equal. Once you know these two quantities are equal, you can immediately find out this formula. This beta I of the stock is very important, because these, if you go to stock market, they will always list down the beta of the stocks for every asset, because that tells you that what is the relation between the expected return. So, what is the relation between the expected return and the risk exposure to the stock in vis-a-vis the market portfolio. So, or what is the relation between this particular return on this particular asset and the return on the market portfolio. So, that will tell you that whether should I give more money to this asset or whether I should give less money to this asset, that would decide. So, beta of a stock is a very, very important parameter. Okay. So, thank you, and we start option pricing from the next class.